Perfect. Let's begin. All right. Hi, everyone. Good morning. Lovely morning in Vancouver, raining right now. And yeah, today I'm going to be presenting what has been my work over the past 2 years as a student of Dr. Frank Wood, who is currently present here. So my work over the past 2 years was primarily focused on making computer vision models, in particular image classifiers, learn effectively when you have limited training data. So as I'm sure some of you are familiar with the conventional image classification setting, where you have lots of labeled data, 1,000+ images per category, and you spend hours of computational training on high memory GPUs. And hopefully by the end of the day, you have an image classifier that presented with an image can produce the correct label. In the few-shot setting, we aim to replicate this, but with a twist where we want to be able to achieve reasonable accuracy with very limited data, a 1 to 2 order of magnitude reduction in terms of labels. And we additionally want to do this in a reasonably fast amount of time. And we still want the end result to be an image classifier that, given an image, produces the correct label. Now, this has widespread applications. One of the cases that we experimented with at Dr. Wood's group was with respect to using this for COVID-19 detection from chest X-rays. At the time, there were 80 or so examples available. And we tried using our work on facial learning to help us there. But there are, of course, other examples, medical imaging cars. Someone's mic is on. If you could please turn it off. Thank you. And these are some of the, and there are widespread industrial implications if we can do this effectively. So at the high level, our problem domain is we have a bunch of tasks that come with limited labeled data. And we have a set of unlabeled data, which we want the labels for. And we have a number of these tasks, and we hope to do very well on all of them as they come along. So to add a bit of notation, we consider that most image classification tasks can be grouped together as a distribution over these tasks. And we define a support set representing the limited number of labeled examples we have, and a query set representing the unlabeled examples for which we want to have a label for. Now, I may throw words such as shot and way during the course of this presentation. By shot, we basically mean the number of classes in the task we're looking at, and by way, we mean the number of classes in the task we're looking at, and by shot, we mean the number of labeled examples we have per class. And so given this support set, our goal is to perform accurately on the query set of images we're given. And so, as I explain later, we propose two methods, one for the standard facial learning setting and the other for the transductive setting. And in the latter one, which is a transductive setting, we have this additional assumption that we get the query set, all those images all at once. So there's opportunity for unsupervised or semi-supervised learning. Now, the fundamental motivation behind our work, and that's what I hope is the key takeaway today, is that if you think about the way linear classifiers work, we are fundamentally learning class representations, which could be described as a row of weights belonging to that class. And then we're specifying a metric by which we're deciding how close this example is to each class representation. And when we start thinking this way, then there's a natural question to ask, can we do better representations and can we do a better metric? And that basically brings us to this work. Two methods that we have proposed over the course of 3 papers for effective and accurate facial learning, both of which stem from the idea of using a regularized high-dimensional Mahalanobis-distance for decision making, as well as a number of other details. Now, these 2 methods achieve state across together. One obviously came later than the other. But both of them at the time of publishing achieved state-of-the-art performance on the Meta-Dataset benchmark, which is the increasingly accepted benchmark, and the more widely used mini and tiered-ImageNet benchmarks. There's actually also a lot of theoretical work. Now, I should give credit where credit is due, and this theoretical work in terms of both modeling both methods in the context of Bregman clustering and in Riemannian method trending. This was done by my co-authors, primarily with Waden and Dr. Van der Ment, doing most of the work on Bregman clustering, and Jared Barber, who is the second author on the second two batch of papers listed, who led the work on Riemannian method trending. And lastly, we also evaluate both methods in the context of out-of-the-box active and continuous learning. Now, I will define active and continuous learning in more detail, but these are some natural settings where we might want a future classifier to work. So as a brief overview of the related work, there has been a lot of work in this area, an enormous amount on future learning. But broadly, we can group them together across two dimensions: how they go about adopting the feature extractor, and how they perform, what metric they choose to perform the classification. And so as you can see, our work on simple synapse and transductive synapse are among those that continue the tradition of using partially adopted feature extractors, where only parts of the feature extractor are adopted based on the new task and its support set. But and there has been a few works before that have attempted this, but we uniquely are able to use the Mahalanobis-distance as our classification metric and do it effectively, such that we gain a significant performance boost. Now, the two works that are probably closest to our work are that of Synapse, which, as the names of the methods I discussed suggest, we directly build on. Namely, we develop simple synapse, which is the next iteration of synapse, and then transductive synapse, which is that method extended to the transductive setting. And so I'll cover synapse in much greater detail. On the other hand, we have prototypical networks, which was kind of the primary paper that put up the idea of let's think about metrics and what we can do. And their work in particular focused on using the Euclidean distance as the decision-making metric. Now, as the figures show, there are several disadvantages in using the Euclidean distance, and the Mahalanobis distance is a general form of the Euclidean distance, but you can also incorporate cluster covariance into the decision-making process. So you could, have a particular feature dimension that represents, say, object color, and a class that's fairly color agnostic. Well, then you should be, have a broader variance allowed for that dimension, and therefore not penalize incoming examples the same way. Now, as I've said, I was going to, cover a brief overview of active learning. In active learning, basically our goal is that we have an unlabeled data pool, but we have the option to request labels for a number of them. So you can think in a medical imaging setting, you have a lot of unlabeled data, and labeling is expensive. So you want to pick the labels that help you boost performance the most. And at each iteration, the model can self-adjust and request a new label for. Now, there are a number of different strategies, and our work in particular focus on uncertainty-based strategies, where you request labels for examples you're most uncertain about. But there are also diversity-based methods, which consider how many examples from each class or feature distribution you have, and also expected model change, where you want to select examples such that the change to the model is maximized. And of course, there are hybrids among them. And a natural baseline in this scenario would be to just go for random selection, randomly pick examples as they come. Now, with continual learning, there has been also a lot of work, and I wouldn't be able to do justice to them if I tried to, cover bits and pieces there. But as a rough overview of what the problem domain is, in continual learning, at each time iteration, you get a new task consisting of potentially new classes, new examples, and new test examples to perform on. Now, the goal is to be able to perform on these new tasks as they arrive without forgetting the knowledge gain on the previous tasks. So you can still maintain performance on those previous test examples. Right, so now let's dive deep into the method. As I told you, our method directly builds on the work out of Cambridge that was conditional neural adaptive processes. Now, at a higher level, the feature extractor in this setup is conditioned to update itself based on the support examples provided. So as you can see, there is this element called the task encoder that groups all the support labeled images you have together and creates a task representation. And then we have this adaptation network that condition on this task representation goes and modifies specific weights across the feature extractor. So when training this, we train the feature extractor separately on a different, general image classification task. In our cases, we use the ImageNet or subsets of ImageNet. But then it is augmented with film layers, and these film layers are able to scale and transform the different feature outputs out of each block. And so by modifying these film parameters, you can think of it as adopting this feature extractor function in a way that it produces a feature space at the end, such that classification can be more optimal. Now, at the classification step, CNAPS continues this idea of using neural adaptive processes, and it also uses, groupings of class means followed by a neural network that then produces weights on a linear classifier that used to actually perform classification. Now, their work in terms of providing these ideas as to how you can partially adopt the neural network using task encodings and class encodings at different level, that was pretty transformative. But in our work, we show that on the classification end, you can actually do better with fewer parameters if you were to use a metric that's more suitable for this task. And so in our work, we consider the Mahalanobis-distance, specifically the squared Mahalanobis-distance as that metric. So kind of putting it in terms of the math, basically, we consider the negative distance, the negative Mahalanobis-distance specifically, to each cluster mean K, once all this support examples have been distilled into these clusters after being pushed through the feature extractor, such that those cluster means are the mean pooled average of the feature vectors of the support examples belonging to each class. And we additionally have this precision matrix term here that is formed out of a hierarchically regularized representation of the covariance for that class. And how do we calculate that? We basically have three elements. The first one is the directly calculated covariance for the class using the class examples. Now here, we just use the closed form definition, and that would be sigma k. Then we have this higher level, which we call it the task covariance, which can act as a hierarchical regularizer on top of this lower covariance. And here we use every example in the task to calculate this sigma. And then lastly, as you can understand, we're dealing in the 512 dimensional space, but we have often, 20 or fewer examples per class. So both of these matrices are going to be low rank, but we need to invert them. So we add this additional identity matrix to assure that they're invertible. Next, we further extend this framework to the transductive domain. In the transductive domain, we first look at the task encoder to see how we could transductively extend the feature extraction adaptation process to also include the unlabeled examples. So what you see on the left, the call variation, is what we do in Transductive CNAPS when labeled examples are available. Basically, there's a two-layer, there's this encoder CNN, which is shared with what the task encoder worked with CNAPS and simple CNAPS. But then we have this count agnostic pooling step that makes sure every class contributes to this embedding equally. And then additionally, we have this second element that looks at the query examples, since in the transductive setting, we get them all at once. And then these query examples, after being processed by the same CNN, the same feature extractor, they're mean pooled to form this query set embedding. And then the two of them are processed in a two-step LSTM to create the final task encoding that then we use in the adaptation network to adopt the entire feature extractor. Now, at the classification level, we also extend the transductive idea by performing semi-supervised clustering. What do I mean by that? Well, if you remember from the earlier talk on simple synapse, we mean pooled those examples and also produced closed form covariance estimates for each class using the examples that belong to that class. Well, now we have a whole bunch of unlabeled examples. And the core idea here is for those unlabeled examples, we could use the class probabilities produced by the model itself as soft labels when performing both the mean pooling for the class means and the covariance calculation for the covariance estimates. And basically, the single update is now instead of weighting every class equally, we introduce this weight W, or responsibility for those of you familiar with EM, where this is quite similar, or Bregman clustering for that matter, such that if the class actually, if there is a label present for that particular example, we set that weight to 1 if the class matches and 0 if the example doesn't belong to the class. Otherwise, we use the model produced probability as the soft label. Now, obviously, you know, the earliest work that kind of explored this idea did it only at one step, but we can now expand this and do soft clustering within the space. So, you know, during each iteration, we first assign these class probabilities based on the current state of the model, where the class cluster lie and how's the distance to each of the unlabeled examples. Then we use these soft labeled examples to update those very cluster parameters. And then we repeat this process until either we hit our minimum or maximum number of steps. So like we hit at the very least the minimum number or the maximum number that's predefined, or we hit a termination criteria, which we define to be when, you know, further steps, when it happens if the most probable class for each query example hasn't changed. And by that, we mean that if one more refinement of these cluster parameters won't have any impact on which cluster the unlabeled examples are assigned to, which is an implicit criteria for measuring convergence. Now, with respect to active learning, we consider the case of out-of-the-box active learning. So we say, let's train these models on the diffusion learning task, where we just give them a number of tasks, and then we train to maximize classification accuracy on the query sets of those tasks. And then we say, well, let's take those checkpoints and try to apply them in an active learning setting out of the blue. And you know, in an earlier slide, I talked about how active learning focuses on class probabilities for the unlabeled classes, unlabeled examples, and it tries to, you know, use different strategies to select which unlabeled example to request a label for. Here we consider 3 strategies: random selection and uncertainty-based methods. Now, the 2 uncertainty-based strategies we consider are predictive entropy, where we select the example with the greatest entropy, as measured by each class probability times the log of the probability, and variation ratios, where we measure, where we rank every example by the lowest class probability they were assigned from any of the classes, and then we select the example with the highest value there. So it's an implicit form of measuring how uncertain they are. And our goal here is to primarily see how simple synapse and transductive synapse are effective at modeling uncertainty, and whether these strategies are more effective than random selection. We also consider this in the context of out-of-the-box continual learning. Here, as I said, at each time iteration, you know, T in our notation, a new task arrives with a bunch of labeled examples that belong to either previous classes, the previously seen classes, or entirely new classes. And our goal is to do well on the test examples of all these tasks going back, going well into the back. And so the goal is to not forget that knowledge. And so we modify our methods in 2 ways. First, we modify the way classification parameters are updated. And that is, we use this kind of convex combination based on the number of class examples already seen versus the number of class examples that have come in during the current task at hand. And we use a convex combination of both the mean and the covariance values we had previously and the estimates from the new examples. So this is done in the part here, in the upper half of the slide. And obviously, if the class is entirely new, this part would be 0, and the entire focus would be on the estimates that are coming from the current examples for this novel class. Now, this is for refining the cluster parameters at the classification level, but there's a big question of, our model and part of its advantage is about how it adopts the feature extractor and that feature space to do classification. And so, and much of that adaptation process relies on the task encoding produced for the task. And so how do we modify that task encoding as these new tasks come along, such that we don't lose information of the past, we can still do reasonably well on the previous test examples, but we also can do very well on the incoming tasks. And here we consider 3 encoding strategies. First, the moving encoding, which is that the task encoding is set based on each task at hand, and the task encoding of the previous tasks are forgotten. And this worked, reasonably okay when the experiments were conducted with CNAPS. But in our case, we observed that our method and the way we train that adaptation network results in vastly different feature extractors and a massive loss of performance if we keep adapting it to the new task at hand. We also consider the first encoding, which is that we just take the first task, we adopt the feature extractor and then fix it right there. And we don't care about adopting the feature extractor for the subsequent tasks. And then we also consider the averaging encoding, which is that similarly on the basis of how many tasks we've seen and the tasks we're looking at, we perform a convex combination of the task encoding for the current task and the averages of previous tasks up to that point. This could be thought of as a similar form of exponential averaging for these task encodings at hand. Right. So before we get to the experimental results, I think it's very nice to kind of review some of the theoretical motivation behind this work that, again, Wayden, Dr. Jan Willem, and Jared produced. So an interesting way to think about what we're doing is that of Bregman soft clustering. So for those of you that are familiar with Bregman functions, there's a difference of 2 convex functions used as a distance metric. And the Mahalanobis-distance is itself a Bregman function with that internal function set to this here. Now, the reason why we kind of try to formulate this Bregman soft clustering perspective is that our work is also very closely related to Gaussian mixture modeling, but not quite. There's a raised hand, but I think that may have been an accident. Yeah, okay. If there are no questions, I'll continue. Right, and so we have this kind of like motivating our work as a Bregman self-clustering procedure that uses Mahalanobis-distance as that Bregman function, as that Bregman distance specifically, and uses it in the context of doing soft clustering. So, you have the label examples, we have the unlabeled examples, and we are doing that kind of, iterative refinement using that metric. But our work is also very closely connected to the Gaussian mixture modeling scene, but not quite. For those of you that are familiar with Gaussian mixture modeling, we have these effectively Gaussian clusters. And if you were to do then inference to assign a new example to a particular cluster, you would use the probabilities produced by those clusters. Now, this is actually different because if you remember, we used just a negative squared Mahalanobis-distance. But if you were to do this the Gaussian way, we have to introduce this -1/2 term. But additionally, we have to especially introduce this -1/2 log determinant of the covariance there. And that's because probabilities in the Gaussian sense, they have to sum to 1. if you were to integrate them. But in our case, they clearly don't, since we don't have this normalization factor. And so we kind of wrestled quite a bit with trying to. I just got a notification that people can see my application. Hopefully nothing has changed. If it has, please let me know. So we experiment with this, and empirically we see that the introduction of this negative 1/2 log determinant term actually results in worse performance. And we kind of, this is one of the main items that we motivate future researchers to investigate why this happens. Now, there was also a very extensive work done by Jared on Riemannian method learning. It's very detailed work on how this could be an alternative perspective on why our method works and what might be happening deep under, within the manifold of the features in the adapted feature space we deal with. I encourage everybody to go and read that. But since, Jared pretty much single-handedly carried this work, I'll kind of, give you guys to read it from his writing. Right, so now let's talk about experiments. As I told you guys, we achieved state-of-the-art performance on Meta-Dataset, mini and tiered-ImageNet. I think it's important to define what these benchmarks are. So Meta-Dataset consists of 10, and almost every paper, including ours, adds 3 additional ones, namely C410, C4100, and MNIST. And all these datasets are grouped together, and different, few-shot tasks where you sample a few examples for, you sample a number of classes between 1 and mostly 20, but it can go up to 100. And you start sampling then images for each of these classes, such that on average, every class has fewer than 20 images per class. And so you build these massive numbers of few-shot image classification tasks across these 13 tasks and 13 data sets. And then you maintain a separate set of classes and images for test time performance, such that once your model is trained, you can then measure test time accuracy on few-shot tasks generated from previously unseen examples across unseen classes across all of these data sets. And a few of these data sets, namely traffic sign, MS COCO, and the 3 additional ones, are kept out of the main, such that the model is also pushed into being able to handle the domain shift that happens from moving on to these types of examples. And so for and there's of course the mini and tiered ImageNet benchmarks that are more older. These are subsets of the larger, more famous ImageNet data set, with a mini ImageNet something around 70 of those classes left, and tiered images something around 600. Again, a set of classes are maintained for training, and a set are maintained for testing. And during training time, we sample tasks from these classes, few-shot learning tasks where you have few examples for those tasks. And then we evaluate the model on the query examples that have also been sampled, and we use the classification loss to backpropagate and learn the network. And in terms of training, we train on the Meta-Dataset for around 110,000 tasks and around 20,000 tasks on mini and tiered ImageNet. Now, in terms of experiments on Meta-Dataset, as you can see, Transductive CNAPS establishes the state-of-the-art overall. And simple CNAPS at the time of publication, it also established state-of-the-art, but now it ranks 4th on the benchmark with an average rank of 3.2. Now, an interesting observation to make here is that all these data sets from ImageNet up to Flower, these are in-domain data sets. That means that during training, we have access to a subset of classes from each of these data sets to sample tasks from and train with them. But this half, these are out-of-domain data sets. These are data sets that in no shape or form have we seen any classes during training from. And it's interesting to point out that transductive CNAPS and simple CNAPS perform much better than other baselines, including some of the work that was developed in parallel on these out-of-domain tasks. And so it might be suggested that in some sense, these methods are able to generalize much better to tasks that come from outside of the training regimen than some of the other work that I've kind of, hammered down on specializing on the data sets at hand. Next, we also evaluate both methods on mini-ImageNet and tiered-ImageNet. Now, here we consider two cases. I should have probably noted that in the previous case, as I told you, our method consists of a feature extractor and an adaptation network and film layers that are then set inside of this feature extractor. Now, on Meta-Dataset, we just trained that feature extractor as a fully supervised classification task on the training split of this ImageNet element in the Meta-Dataset we have. In the mini/tiered-ImageNet setting, it gets slightly more complicated because there's a big question of like, well, what do we train this feature extractor on? And so we consider two cases. The first one, which we simply just call as the method, we take all the training classes and examples that we have for each benchmark, and we treat it as a fully supervised multi-class classification task. And then we train our feature extractor that way. Now, an interesting thing that you would observe almost immediately is that if you look at the performances, well, they're not as competitive as we saw on Meta-Dataset, but specifically, the performance on the tiered-ImageNet dataset compares much better against baselines than it is the case with mini-ImageNet. And this goes to show that it's really important for us to have a densely trained feature extractor that has seen a fairly diverse number of data points for our method to perform well. And on the tiered-ImageNet side, we have enough training data to achieve that. But on the mini-ImageNet side, our feature extractor might start to overfit and therefore performance is lost. Now, to kind of experiment this further, we considered this plus FETI, F-E-T-I variation, where we train that feature, we take the ImageNet, we exclude all classes that belong either to the test set of the mini-ImageNet benchmark or the test set of the tiered-ImageNet benchmark, but we keep all other classes, about 850 or so. And we train our feature extractor on this now larger, more densely populated dataset. And as we can see, then our model is able to perform the best across the board. And we similarly see transductive CNAPS performing better than simple CNAPS. Now, it's also interesting to look at how class recall works versus class shot. It's an interesting observation. Let's first focus on 6.1b, which we look at the non-transductive case. We see that those hierarchically produced high-dimensional covariance estimates that they're 512 dimensional and are pulled from few examples. They can produce superior performance to that of both the original CNAPS model and even replacing it with the squared Euclidean distance with as few as 4 examples per class. Now, below 4, we suspect that there are too few examples for this covariance to make any sense, and so performance degrades. But it's frankly quite astonishing that this works with even as few as 4 examples at that level. Now, on the simple versus transductive case, that's figure 6.1a, we see that the transductive cluster refinement process actually helps performance quite a bit when we have 10 or fewer examples. And so this is where you have too few examples, and any kind of self-supervised, semi-supervised refining can help you establish better clusters that are then more accurate when classifying. But on the other hand, when we start going above 10 examples per class, the class shot specifically equaling 10 or more, we start seeing that transductive CNAPS actually starts performing worse than simple CNAPS. So that semi-supervised refinement process is now a bit more noisy and distractive compared to where it was before when we were dealing with 10 or fewer exams. Now, in terms of metric ablations, hopefully I got the pronunciation right this time, we consider the case of, we have the squared Mahalanobis-distance and we replace the CNAPS classification framework with that, but could we do any other metric that could potentially be better? And we consider the negative dot product. Now, the negative dot product can very much be thought of as just doing linear classification, because that's the process, and using it, it's the negative distance used. So the negative of the negative is effectively the dot product being performed. we consider the cosine similarity as the distance metric. We consider absolute distance. So, you know, the absolute value of the distance between the two in the space. And we, of course, consider the squared Euclidean distance, which is fundamentally a more narrowed down variation of the Mahalanobis-distance, which assumes identity covariance. And we once again see that the squared Mahalanobis-distance performs much better than all other variations considered, both on in-domain tasks and out-of-domain tasks, and of course, overall. Now, we additionally evaluate these models to you know, understand different aspects of them. So we first, you know, if you remember earlier in our discussion about the theoretical motivation of this work, we looked at how our work very closely it's very similar to that of Gaussian mixture modeling, but not quite. Specifically, there is not the log determinant of the covariance normalization factor. So in the first two top rows, we consider two ablated variations of simple and transductive synapse that enforce that exact equation for classification. So we introduce the negative log determinant. And what we observe, and you know, we call the first variation GMM, which corresponds directly to simple synapse with Gaussian specific probabilities production. And then we consider GMM EM, which, you know, when you enforce the exact matching to Gaussian mixture models, then our soft k-means clustering procedure turns into expectation maximization. And what we see is that the introduction of that term generally results in worse performance, which is interesting because it suggests that there's some behavior in that log determinant term that is not aligned with how the feature extractor is forming the feature space. Now, additionally, we consider a number of other things. First, in the transductive synapse setting, we actually don't perform the soft k-means clustering part during training the model. We're performing when we're evaluating at test time, but we don't train with that on. And that's because, as we, you know, empirically observe, this results in worse performance because, especially during early iterations of training, the gradients coming from those soft labels can be very noisy, and you might have a number of examples that are assigned to the wrong clusters. And that performance results in potentially suboptimal paths to convergence. Now, lastly, we consider these FEOT and COT model variations. Now, FEOT stands for feature extractor only transduction, and COT stands for classification only transduction. And here we just take transductive synapse, and we want to see whether our, you know, transductive task encoder, which was our modification to the feature extractor, is responsible for the performance gain, or the soft k-means classification refinement procedure. And as we see, both are in different ways responsible for the performance gain. So both of these variations perform better than simple synapse, signifying the gain in having both of them. But additionally, they both perform worse than transductive synapse, which goes to show that together they're leading to a considerable amount of the performance gain observed here. Now, coming to active learning, we consider the CFAR10 and OmniGo languages benchmarks. Here, a number of the examples are pulled together into this unlabeled data pool. And a number of these examples are then given to the model with labels for the first step of model adaptation. And then at each label acquisition iteration, we can request a label for one of those unlabeled examples that we've seen. And as previously said, we consider three cases: random selection, where we just select an unlabeled example and request a label for at random; predictive entropy; and variation ratios, both of which were uncertainty-based methods, where we looked at how uncertain the model is about a particular example, and then requested labels for the most uncertain example. Now, what we can see, and I want, you know, are three major observations. Unsurprisingly, transductive synapse performs better than simple synapse here. Both methods perform better when running with uncertainty-based methods than when running with random selection, which goes to show the fact that they're able to perform, they're able to create reasonably accurate models of uncertainty, of example uncertainty. And then the third thing is the lines for simple synapse are more wider apart than those for transductive synapse, which goes to suggest that transductive synapse might actually be recovering much of the performance gains that comes from having those labeled examples through its semi-supervised clustering procedure. Now, as for continual learning, we compare, again, out of the box use of both simple and transductive synapse in a continual learning setting on MNIST CIFAR10 and CIFAR100 benchmarks, where you get effectively 100 shot per category tasks. So, for instance, for MNIST, the first task is digits 1 and 2, 100 label examples for each, and a number of examples for test time classification. Task 2, now there are digits 3 and 4, and you have these 5 tasks, and a similar setup with CIFAR10 and CIFAR100. And what we see is that obviously we don't perform as well as some of the previously proposed methods, random walk, BCL, EWC for continual learning, but also that we don't perform as well as Synapse, which their modification also uses the moving encoding approach, where you take the task encoding of whichever task you currently have at hand. This to some extent, at least when I was personally looking at it, goes to show how significant is the change in the feature manifold after the feature extractor has been adopted in our models versus Synapse and the other works. And that's because, as you can see, moving encoding almost entirely destroys performance, because the previous examples are now in different parts of the feature manifold of the new task at hand, and so performance really degrades considerably. I have a second slide which goes into more details right after this, but also we should note that the averaging encoding strategy is the one that performs the best. It kind of balances a good balance between adopting the feature extractor to an optimal space, adopting the feature space to an optimal space such that classification can be performed on new tasks without completely forgetting the knowledge of the previous tasks. Right. So this is the slide I was referring to. Here, and I should have probably defined multi-head and single head. Multi-head, it means that we can assume that we have a separate head of classification for each task at hand. So for instance, when we are at task 4 on MNIST, we don't go and we want to go perform on the test examples of task 2. We can assume that when we're performing on task 2, we know that we're performing on task 2, so we're only considering the classes belonging to that task. Whereas the single head assumes that all classes are up for classification. So here we compare the test example classification accuracy on each of the classes and tasks on MNIST throughout the 5 continual learning iterations, using each of the different head strategies and different encoding strategies. And what we observe is that for the moving rep, the moving rep, in the multi-head simple classification, simple synapse classification task, the performance starts to degrade, and it generally benefits the very last task at hand. And this is understandable because you're adopting your feature extractor on the task encoding of the very last task. So that is the best position task to perform well. In the single head setting, the performance is almost entirely eliminated for the previous task, because the new manifold is so specialized onto the new task at hand. It can, it's pretty much unable to recover any of the previously learned knowledge. Now, with respect to first rep encoding, we see that the first task is, I think someone's mic is on. I'm gonna quickly mute it. We see that the first task is often the best to perform. And that's again understandable, because in the first rep encoding strategy, we set the task encoding to the first task during adaptation of all tasks. But the performance is reasonable on the other tasks. Now, with the averaging encoding, we see sort of the the relative best of both worlds, in the sense that in the multi-head case, the performance is actually the best and the most distributed across all the tasks at hand, without any particular favoring towards one task or the other. But in the single head case, we actually see worse performance because in first encoding, we at least have a fixed feature space that we're dealing with. But the rapidly changing feature space, especially in the context of simple and transductive synapse, can mean that the manifold is changing so much that the distances within that space are now arbitrary for previously seen testing, for the test examples of the previously seen tests. Right, okay, so fortunately I did faster than I was expecting. So as a brief overview, throughout this thesis, we kind of tackled the issue of, well, can we do feature learning and label efficient learning of image classifiers? And then we explored how these models can work within a number of settings. And so the two models proposed were simple and transductive synapse. They both achieved very competitive results, with transductive synapse achieving state-of-the-art on a number of benchmarks. We evaluated both methods for active and continual learning and indicated some very interesting patterns. And this kind of brings me to what I hope that the past 2 years of my life maybe motivates others to do, which is for one, we have a very interesting observation of high dimensional covariance estimates based on few examples actually working really well. And this may suggest that the way the feature extractor adaptation network is being learned is resulting in manifolds that make that high dimensional, but based on few example covariance estimate very useful. And so better theoretical understanding of this framework can potentially result in greater boosts and better directions in how to empirically take this research forward. Now, another direction, and I kind of tackled this slightly, but perhaps not as much as I should have, is to explore ways we could potentially use, especially the probabilistic clusters form, to generate additional examples. Whether it's about augmenting the support examples we get or generating entirely new examples. And there is a number of great works that have been done in this area, but I think there's still a lot of potential left. Now, improving cluster refinement algorithms with respect to both methods can prove to be also very fruitful. And additionally, better feature manifolds for continual learning, or better rather strategies for adopting said feature manifolds for continual learning, can also go to alleviate a number of the issues we saw when evaluating on continual learning benchmarks. So now, lastly, that kind of concludes my presentation, and I'm of course more than happy to answer any questions. I wanted to take a moment to thank pretty much all of you who are currently on this call, especially Dr. Frank Wood, who was my supervisor, and Dr. Leonid Siegel, who has in many capacities stepped up as my second reader to get this work done. And this would have not been possible without you, especially the two of you, and of course my family and friends and colleagues, all of whom are also friends, who are currently on this chat. And so I appreciate all of you, and it's been a true privilege and honor to have done this work with you. I'm happy to answer any questions.